Welcome to this 13th lecture of this lecture series on design principles of RF filters and amplifiers. We were discussing RF amplifiers, and we have said in the last class we have seen that depending on the S parameter values, sometimes we have unconditionally stable devices, transistors. Sometimes we have potentially unstable devices. So, we need to choose proper load impedance and source impedance, so that we can make the device conditionally stable. That means, a range of values of gamma L and gamma S or ZL and ZS needs to be defined, for which the amplifier will be stable. So, today we will see that, and then we will see that is there any simplified way of finding from the S parameters whether the device is unconditionally stable or potentially unstable. So, we can recall that in a loaded transistor amplifier, that means if I have a transistor with its S parameter known and impedance level Z0, we will connect a source similarly we will connect a load and we have seen that depending on the impedance level here, there will be reflection coefficients both sides, that means towards the source, that is called gamma S. There will be gamma S here, there will be gamma in here. Similarly, here there will be, depending on the mismatch, in general there will be gamma L and there will be gamma out. Also, we have seen various gain definitions, etc. We have seen that transducer power gain will give us the actual value of the power that is dissipated in the load divided by power available from the source. That ratio, that means in the loaded condition, the transistor, the full system, its power gain, that is the useful criteria which we will try to maximize finally and achieve a amplifier design. Now, last day we have seen that obviously our gamma L and gamma S, that means the corresponding ZL and ZS, they are passive. So, they should lie within the Smith chart, unit circle in Smith chart, and gamma L, gamma S, they should be also within the Smith chart with unit radius, normalized Smith chart with unit radius, and we have seen that gamma in is given by S11 plus S12 S21 gamma L by 1 minus S22 gamma L, that we have already seen, and we demand that the device to be unconditionally, or whenever potentially unstable, also to be conditionally stable. We require that gamma in, that means this should be less than 1, and also gamma out, that is S22 plus S12 S21 gamma S by 1 minus S11 gamma S. This also needs to be less than 1, otherwise we will have oscillations. So, now which range of gamma L and gamma S will enforce this condition, that we will see. To do that, we see a Smith chart, there we will find out that actually you see the border region from here is that gamma in, if it is less than 1 it is conditionally stable, but if gamma in is greater than 1 it is unstable. Similarly, gamma out magnitude less than 1 it is stable, conditionally stable, and gamma out greater than 1 it is unstable. So, this leads us to say that basically the border region is this, that gamma in is equal to 1. If we can locate this locus, similarly gamma out magnitude is equal to 1, then we can divide the whole Smith chart into two regions. One will be stable region, another is unstable region. From the stable region we will choose our gamma L and gamma S. So, this the boundary between stable and unstable region in a Smith chart is given a name. It is called the stability circle. Why circle? We will just now see that it ultimately turns down to be a circle, this locus. So, this boundary, that means locus of all these boundary region, the boundary points, that becomes a circle, that is called stability circle. So, in the this Smith chart we can consider this as a both as a reflection coefficient plot as well as the corresponding impedance plot. So, in the reflection coefficient plane we can say that stability circles are nothing but locus of gamma in is equal to 1 or gamma out is equal to 1 in reflection coefficient plane of the Smith chart. So, that means we have two such locuses. So, we will have two stability circle, one we call output stability circle, that means which determines the values of gamma L that gives that boundary. That means, for gamma in is equal to 1, as you can see that gamma in is basically a function of gamma L as well as S parameters of the transistor. So, this output stability circle is when gamma in is equal to 1, that we call output stability circle. Similarly, gamma out is equal to 1, that we call input stability circle, because this depends on the choice of source impedance or gamma S, reflection coefficient gamma S. So, there are two stability circles now. Let us see one by one. Let us first see the output stability circle. So, output stability circle is given by gamma in magnitude is equal to 1, that implies we have S11 plus S12 S21 gamma L by 1 minus S22 gamma L is equal to 1. Now, this we can, now this equation we can manipulate. Remember, these S values all are S parameters and gamma L, they are complex numbers. also we can define this quantity gamma is the determinant of the S matrix. So, gamma is nothing but S11 S21 minus S21 S12. In general, gamma is also complex. So, this if we just manipulate this and if we solve for, because you see this is one equation where S11 S12 S21 S22 are known quantities, gamma L is unknown quantity. So, we can solve for gamma L and that gives that gamma L minus S22 minus delta S11 star whole thing star or conjugate divided by S22 square minus delta square. So, you see this is simple manipulation, remembering the quantities are complex. So, gamma L can be written as gamma L is equal to this is a real number because this is magnitude of the whole thing plus this complex number magnitude. So, in the complex plane, in this complex plane, this represents a circle, because you see that this is of the form, I can write it as a form that gamma L minus some, this is a complex number. So, CL it is a complex number is equal to some real value. So, that I can say as RL. So, this represents a circle, that is why the name output stability circle. So, here CL is the center of the circle, RL is the radius of the circle. So, we can say that output stability circle this circle is has a center at CL is equal to S22 minus delta S11 star whole thing star divided by S22 square minus delta square. This is the center of the circle. You know that for a circle, if I know the center and radius, I can draw the circle. So, knowing the S parameter values or measuring them, I can find what is this circle. This is the radius of the circle. Similarly, I can have input stability circle, which will be given by gamma out is equal to 1. Again, gamma out you know is a function of gamma S. So, with that we can find out that gamma S, if I properly rearrange, then gamma S minus C S is equal to R S. This is the locus of the circle of the input stability circle, and what are these values? C S turns out to be S11 minus delta S22 star, star means conjugate, and R S is S12 S21 by S11 square minus delta square. This is the center of the circle, this is the radius of the circle. For memorizing, you see that CL, the S22 is replaced by S11, S11 is replaced by S22 here, S22 is replaced by S11, similarly this S22 is replaced by S11. So, the equations are similar. Now, what these circles do, that means if I have a Smith chart, if I have a Smith chart like this, then the stability circles, there are various choices. One thing can be stability circle is completely outside. If this is the stability circle, that means you see that they are not intersecting. Also, I can have, instead of this, another thing, that stability circle is like this, it is completely enclosing the Smith chart, or the third choice is the stability circle is intersecting with the Smith chart. So, let us first see that intersection part. So, if we have this intersection 1, let us say this is the output stability circle with somewhere center CL and radius RL. Now, what it says, this is the output stability circle. So, you see that this one has divided this whole Smith chart into two regions. One region is this portion and another region is the one that is inside this circle. Now, since this is a boundary, this output stability circle means this is the locus of the point gamma in is equal to 1. So, I know that one of these, either this region or this region, will be unconditional or conditionally stable and another region is unstable. Now, I will have to determine which region is stable and which region is unstable. So, for that, let me draw this, that suppose this is my Smith chart and this is my, let us say, output stability circle. Now, what I do, now there can be two cases, that suppose first to determine that which one is stable, whether this region is stable or this region is stable, what I need to do in my thing, if you see that, let me make a choice in my mind that ZL is equal to Z naught. That means, I am choosing the load impedance, choosing this load impedance same as Z naught. If I do that, immediately I can see that gamma L will become 0. So, ZL is equal to Z naught makes gamma L is equal to 0, and then I can see from this expression that if gamma L is equal to 0, gamma in magnitude becomes S11 magnitude. So, this is one of the choice, as we have seen in simple matching we do it, instead of conjugate matching I can do this, and in that case you see gamma in becomes S11. Now, there can be two possibilities, this gamma S11 magnitude that can be less than 1 or greater than 1. Let us say case 1, when it is S11 is less than 1, sorry, S11 is less than 1. Now, if S11 is less than 1, immediately I can see that, or let me write here, that gamma in this case becomes less than 1, which was my condition for stability. So, that means, and where this point lies, you see gamma L is equal to 0, this point will always lie at the center of the Smith chart, and I know that in this region at this point gamma in is less than 1. So, this is a stable region. Immediately I got my answer that this is the stable region of the Smith chart. So, I can say this is a stable region, and obviously this one, that means this portion of Smith chart is unstable. So, I will choose my gamma L from the stable region, then I will enforce that the input side is stable. Also, now there can be the second case, that case 2. Case 2, what is case 2? That S11 value, I do not have any play with this, because manufacturer has given this, it can be greater than 1. If it is greater than 1 and I have made this choice that ZL is equal to Z0, so I immediately see that gamma in again becomes S11, but this time it is greater than 1. So, I know that this choice that gamma L is equal to 0, this point lies at the center. Let me again, so this is for this case, let me again draw this. This is my Smith chart, and this is my output stability circle, and this is the point. Now, in this case I see, this is for case 2, this is the case. You see that gamma L is equal to 0 has led me to gamma in is greater than 1. So, this is an unstable region in this case. So, I can immediately say that this zone is unstable, and then I know that this region is stable region. So, here, sorry, not this whole thing, this part inside, because my gamma L should be passive. So, up to this point. So, then I need to choose my gamma L only from this place. If I choose it here, I will get an, instead of an amplifier, it will become an oscillator. Similarly, I can do this whole exercise for input stability circle. Let this is my Smith chart, and let input stability circle is something like this. This is my input stability circle, and that also has divided, you see again the thing here and here, that this portion and this portion. So, I need to now decide. Again I do the same thing, that I find out the, let us take ZS is equal to Z0. That means, here I choose ZS is equal to Z0, immediately that makes my gamma S go to 0, and if gamma S go to 0, I know gamma out is simply S22 magnitude. So, I got gamma out is equal to S22 magnitude, and gamma S is equal to 0. Now, I know gamma S, this is my gamma S is equal to 0 point, and this is S22. So, again there can be case 1, that I have S22 magnitude less than 1. In that case, I know, in case 1 I know that gamma S is equal to 0. So, this is a stable region. So, I can immediately say that this is my stable region, stable, and this portion unstable. So, I should not find my gamma S from here, I should choose my gamma S anywhere from here. So, this is for case 1. Now, I can do the same exercise for case 2. This is my, let us say, Smith chart, and this is, let us say, my the input stability circle, and in the case 2 I know that S22 can have greater than 1. In that case, my with this choice of Z s is equal to Z naught, gamma s will become 0 and gamma out that will be equal to S22 and that will be greater than 1. So, I know that this point of the Smith chart is now an unstable region. So, I will say that this becomes now my unstable region and this is my stable region. So, I should choose my gamma s from here. So, this is for intersection case. As I said that I can also have this, that this is the Smith chart and any of the stability circle, suppose input stability circle is this, output stability circle is this, output stability circle, input stability circle. So, that means there is no interaction here. So, I can easily find out that okay, in this case if I locate that there are no intersection, means the device is unconditionally stable. Similarly, I can also have the case that the stability circle is completely like this, ISC or OSC. In that case also I see there are no interactions. So, no problem, I can have this thing carry on. So, by this, so we can find out that what are the ranges of gamma s and gamma L for which we can have the conditionally stable amplifier. So, we will choose according to that. But the question is that do we need to plot these circles always? That we will see in the next lecture, that always it is not necessary. Sometimes we can simplify just by some analytic expressions, we can find out whether the device is unconditionally stable. If it is unconditionally stable, we need not draw these stability circles, but if it is conditionally or potentially unstable, then we need to draw these and locate these points, locate these ranges of gamma s and gamma L for which I can make the amplifier stable, and so I can use the device even though it is potentially unstable, but for my enforced condition of load impedance and source impedance, it will behave as a stable device, a stable amplifier. Thank you.